Ever imagine, like flying down the tracks at 300 kilometers an hour? What keeps those rails, those seemingly endless rails, from just warping under that incredible heat and pressure?
It's a pretty mind-boggling thought, isn't it?
Yeah, I mean, you'd think there would be gaps built in, right? Like bridges have to account for expansion,
Right.
but there aren't. So how do these continuous welded rails, or CWR as the engineers call them, actually work? That's what we're diving into today, the mystery behind these seemingly impossible stretches of steel.
It does kind of defy our intuition, doesn't it, to think that they're just like one solid piece.
It really does. And our sources for this deep dive are, they take us right to the heart of it all. We've got research papers, firsthand accounts from welding crews, even historical records that kind of paint a picture of how CWR came to be.
It's quite a story, actually.
But before we get ahead of ourselves, let's start with the problem, right? Steel expands when it gets heated. Basic physics.
Absolutely. And there's a formula for that expansion, uh, ALAET. It basically means even a small change in temperature can make a big difference over long distances.
Right. And to give you an idea of the scale here, think about this. A typical 12-meter rail section, it can expand by about 6 millimeters with just a 40 degrees Celsius temperature change.
Hmm.
Now multiply that by, kilometers of track,
Hmm.
and you've got a recipe for, well, disaster, right?
Yeah, a buckled rail. It can mean, well, derailment, delays, massive costs, potentially even lives at risk.
Exactly. So knowing this, how did they even handle this before they had continuous welded rail? I was reading uh, about gapped rails. They used to have these fish plates and bolts to hold everything together.
Ah, yes. The good old days. Well, I guess good is relative. That was the traditional solution, allowing for the expansion and contraction. But it came with its own set of drawbacks, let's say.
Like that iconic clickety-clack sound.
Oh, absolutely. Those gaps, they created noise. They increased wear and tear, not just on the rails, but the wheels too. And those joints, oh, they needed constant maintenance. Tightening bolts, replacing parts, you name it.
So a lot of downsides to what I guess seemed like a simple solution at the time.
Yeah.
Sounds pretty inefficient.
Very much so. And that's where things get, that's where things get interesting.
That's where our hero enters the scene.
Mm.
Thermite welding. Honestly, when I first heard about this, I thought it was like something out of sci-fi movie, molten metal, sparks flying, the whole bit.
It's quite the spectacle.
So how does thermite welding even work? Break it down for us.
Well, thermite itself, it's a mix of iron oxide and aluminum powder. When it's ignited, it creates this incredibly powerful exothermic reaction.
Exothermic, hold on. What's a
Oh, it just means it releases a lot of heat. Like a lot. Enough to melt iron right there on the spot. We're
Yeah.
talking over 2,400 degrees Celsius, no furnace needed.
Wow. That's hot. So they're basically harnessing this intense heat to melt and fuse the ends of the rails together, making it one continuous piece.
Exactly. And the descriptions in our sources, they paint a pretty vivid picture. Welders working in the dead of night, sparks raining down as molten steel pours into a mold, fusing those rails together. Pretty dramatic stuff.
Sounds kind of dangerous too.
Yeah.
Like walking a tightrope between brute force and absolute precision. You've got all this incredible heat, but it's got to be perfectly controlled, right?
Hmm.
Otherwise.
Oh, yeah. The consequences can be pretty catastrophic. The integrity of those welds, it's absolutely paramount. Any little flaw, even something microscopic, it could spread under all that stress from train traffic, leading to cracks and eventually, well, rail failure.
So how do they make sure these welds are, up to snuff? It seems like the stakes are pretty high.
Right. They have really rigorous quality control measures in place. Like after the weld cools, they use these ultrasonic scans to check for any internal flaws or voids. They even do bend tests, subjecting the welded rail to extreme forces just to make sure it can handle the load.
Like they're putting them through boot camp.
In a way, yeah, it's this blend of old world craftsmanship and cutting edge tech, all to ensure safety and reliability.
So we've got these seemingly endless rails fused together with this crazy thermite process. But the big question still kind of lingers, doesn't it? How does continuous rail even deal with that thermal expansion? It seems, I don't know, counterintuitive.
It is, isn't it? But here's the thing. A continuous rail actually absorbs expansion better than those short, gapped segments they used to use.
Okay, now I'm really intrigued. How does that even work?
It all boils down to how CWR distributes stress. Instead of having all those weak points at every joint, the stress is spread evenly across the whole length of the track.
So instead of pressure points at the gaps, it's more like a smooth flow of force.
Exactly. And that's where this concept of neutral rail temperature, or NRT, comes in. This is the temperature they install the rail at, where it's neither in tension nor compression. It's like a perfectly balanced state.
Okay, so NRT is kind of our baseline. What happens when the temperatures, deviate from that baseline?
Well, when it gets hotter than the NRT, the rail goes into compression. When it's colder, it goes into tension. But, and this is the crucial part, as long as the stress stays below the steel's yield strength, it's all good. The rail can handle it.
So it's like the whole track is working together as one unit to absorb and distribute the stress.
Exactly. It's that unified strength that allows CWR to deal with those temperature changes without buckling.
That's incredible. It really challenges like our initial assumptions about how things should work. We've got this super strong continuous rail thanks to thermite welding, and this continuous structure actually helps manage thermal expansion better than those gapped rails. But I'm guessing there are still some challenges, right?
You're absolutely right. While continuous welded rail is this remarkable feat of engineering, it's not without its complexities.
Okay, let's get into those challenges then. What are some of the potential problems engineers have to deal with when it comes to CWR?
Well, one of the biggest headaches is uneven stress distribution. You see, the track isn't perfectly uniform. There are variations in the ballast, that's the stuff that supports the rails, and the ground itself can settle over time. All these little inconsistencies, they create areas where stress is concentrated, even in a continuous rail.
So even though the continuous structure helps distribute stress overall, there can still be these like localized pressure points.
Exactly. And then you've got those extreme temperature swings, especially in certain climates.
Hmm.
Those can really push the rail to its limits. If that stress isn't managed carefully, you could still end up with, well, buckling or even rail breaks.
It's like this constant battle against nature, even with this advanced system. What other challenges are there?
Well, we talked about weld integrity earlier, but it's worth emphasizing again. Any flaw in those thermite welds, it can become a critical weak point under stress. And those flaws can be incredibly difficult to find, even with all the fancy inspection methods they have. It's a big concern for engineers and maintenance crews.
It sounds like a lot of responsibility rests on the shoulders of those welding crews, huh?
Oh, absolutely. They're working in tough conditions, often under tight deadlines. And those welds, they have to be flawless. Lives literally depend on their work. It's a high pressure job, to say the least.
It's kind of mind blowing to think about, the skill and precision it takes to make those welds, knowing what they have to withstand.
Mhm.
But it doesn't stop there, right? Even after it's installed, continuous welded rail needs ongoing maintenance and adjustments, all to make sure it stays stable in the long run.
You got it. It's not a set it and forget it kind of technology.
So what kind of adjustments are we talking about? What keeps these rails running smoothly year after year?
Well, one crucial process is called rail distressing. Remember how we were talking about the neutral rail temperature, how it can shift over time? Those repeated cycles of heating and cooling, they can gradually throw it off balance,
Yeah.
potentially leading to a buildup of stress.
So it's like that baseline we talked about is it's slowly creeping up or down.
Exactly. And that's where de-stressing comes in. They actually cut the rail, allow it to expand or contract freely just to relieve all that built up stress. Then they weld it back together at the new, adjusted neutral temperature. It's like giving the rail a chance to breathe, to relax before locking it back in place.
Okay, that makes sense. But I'm guessing this is a pretty delicate operation. What are some of the things that can go wrong during de-stressing?
You're right to be cautious. Cutting and welding a section of rail that's part of this larger continuous structure, it's not a small feat. Our sources, they really highlight how much planning and precision this process takes. First, they have to figure out how much stress needs to be relieved, and they got to determine the new target neutral temperature.
So there's more to it than just cutting and welding. There's some serious math and physics involved.
Oh, absolutely. They use sophisticated computer models. They take into account all sorts of factors: the rail's original installation temperature, the ambient temperature during the process, even the expected temperature range for that section of track.
It sounds like a giant equation with a ton of moving parts.
It is. And once they've figured out the new neutral temperature, they have to execute the cut and weld perfectly. Any misalignment, any little imperfection in that weld, it can compromise the whole thing. It could create a new weak point.
So the stakes are pretty high during de-stressing. It sounds like a lot can go wrong if they aren't careful.
It can. Our sources actually mention some Some pretty dramatic examples of distressing gone wrong. In some cases, well, incorrect calculations or just improper execution, it's resulted in rails buckling or even breaking right after the procedure.
Yikes, that's not good. So it seems like de-stressing is I don't know, like a necessary evil. It's crucial for the rail, but it also has its own risks.
That's a good way to put it. It's this constant balancing act, you know? And it really highlights how much vigilance it takes to maintain these continuous welded rail systems. It's not just a one-time thing.
It's amazing how much complexity is hidden beneath the surface of what seems like a simple solution. So we've covered a lot of ground in this first part of our deep dive, haven't we? From those basic principles of thermal expansion to those crazy thermite welds, and now the challenges of maintaining these massive systems. But our journey's not over yet.
Not even close.
In the next part of our deep dive, we're going to take a closer look at this whole process of rail distressing. We'll explore how CWR has changed the railway industry, and we'll even peek into the future of this technology.
Stay tuned. Welcome back to our deep dive into the world of continuous welded rail. It's pretty fascinating stuff.
It really is. We covered a lot of ground last time, didn't we? Tackled that fundamental challenge of thermal expansion and that seemingly impossible solution,
Mm.
thermite welding.
Yeah, we explored those incredible welds that create these endless tracks that can handle these immense forces.
But we also we uncovered some of the inherent challenges too, right? Like uneven stress distribution and how important weld integrity is. It's all connected.
Absolutely. And if you remember, we kind of left off on a bit of a cliffhanger talking about that delicate process of rail distressing.
Like a scene out of a movie almost, you know.
Hmm.
These crews cutting into these massive steel rails and welding them back together. It sounds risky.
It can be if it's not done right.
So let's pick up right where we left off. Can you walk us through the intricacies of rail distressing? What actually happens during this process, and why is it so important for these continuous rails?
It's a fascinating procedure, and our sources they do a great job of breaking it down. As we talked about earlier, the neutral rail temperature, that sweet spot where the rail is, it's neither in tension or compression. It can shift over time because of those repeated heating and cooling cycles.
It's like that baseline we talked about is slowly creeping up or down over time.
Exactly, and if that shift gets big enough, you start to get this buildup of stress in the rail, which can make it more likely to buckle or even break.
So distressing is kind of like hitting the reset button on that neutral temperature.
That's a great way to think about it. They cut the rail, allow it to expand or contract freely to relieve that built-up stress. Then they weld it back together at the desired neutral temperature. It's like giving the rail a chance to breathe,
Huh.
relax a bit before they lock it back in place.
Okay, that makes sense. But I imagine this is a pretty delicate operation.
Mm.
What are some of the things that can go wrong during distressing?
Well, as you can imagine, cutting and welding a section of rail that's part of this larger continuous structure, it's no small feat. Our sources, they talk about the meticulous planning and precision that's required for this whole process. First, they have to carefully calculate how much stress needs to be relieved, and they got to determine the new target neutral temperature.
So it's not just a matter of cutting and welding. There's some serious math and physics involved.
Oh, absolutely. They use these sophisticated computer models, and they have to take into account all sorts of factors like the rail's original installation temperature, the ambient temperature during the distressing process, even the expected temperature range for that particular section of track.
It sounds like a giant equation with a ton of variables.
It is, and once they've figured out the new neutral temperature, they have to execute that cut and weld perfectly. Any misalignment, any imperfection in that weld, it can compromise the integrity of the whole rail,
Mhm.
could create a new weak point.
So the stakes are pretty high during de-stressing. Sounds like a lot can go wrong.
It can, and our sources they mention some pretty dramatic examples of distressing gone wrong. Sometimes, well, incorrect calculations or just improper execution, it's led to rails buckling or even breaking right after the procedure.
It's kind of unbelievable that something so small could have such a huge impact.
Yeah, it really shows how interconnected these systems are and how important precision is at every step.
So it seems like distressing is, I don't know, like a necessary evil. It's crucial for the rail in the long run, but it also comes with its own set of risks.
That's a good way to put it. It's this delicate balancing act. It highlights the constant vigilance that's needed to maintain these continuous welded rail systems. It's not just a one-time thing.
So we've talked about the how and the why of distressing, but can you give us a sense of the scale of this operation? How often does this need to happen, and how much track are we talking about?
That's a great question. The frequency of distressing, it really depends on a lot of factors: the climate, the age of the track, the amount of traffic it sees. But typically, a section of continuous welded rail might need to be distressed every 10 to 20 years.
Wow, that's a pretty long interval.
It is, but remember, we're talking about thousands of kilometers of track all over the world. So even though each section might not need distressing that often, it's a continuous, ongoing process for railway operators. It's a massive undertaking.
It's hard to wrap your head around the scale of it. Thousands of kilometers of track, constantly expanding and contracting.